software teams routinely dedicate months, sometimes years, to mapping out technical architectures before writing a single line of code. Projects frequently fail when the end user rejects the product logic, regardless of how well the code itself executes. The software simply fails to solve the actual business problem. This happens because the initial planning phase relies on the assumption that if a client understands their business, they can accurately state what the software needs to do. Relying on everyday users to articulate their needs with strict technical precision is a primary cause of project failure. A system collapse usually starts at the definition stage. The failure occurs because the initial problem was defined incorrectly. Requirements engineering encounters the elicitation fallacy, the belief that requirements are static objects waiting to be gathered and transcribed. The requirements phase is a load-bearing bridge between stakeholder desires and system design. Handled passively, it faces three structural barriers. First, scope. Ill-defined boundaries cause project parameters to drift. Second, understanding. Non-technical stakeholders create gaps. Finally, volatility. Changing business needs make initial requirements obsolete. To manage these barriers, engineers move away from passive documentation toward active, dynamic systems modeling. Treating requirements as a rigorous engineering discipline provides a mechanism for managing project volatility. Reducing the failure rate requires a move away from isolated one-on-one stakeholder interviews. Software teams instead utilize joint application development, or JAD. JAD establishes a continuous feedback loop. Engineers and diverse stakeholders work together to define the system concurrently. This environment forces the real-time negotiation of conflicting priorities. Issues are identified and resolved during the planning phase. This collaboration produces a library of usage scenarios and agreed-upon technical constraints. Establishing these negotiated boundaries solves the scope barrier by defining exactly where the system begins and ends. Even in collaborative sessions, users rarely articulate their deep-level systemic needs. Engineers apply quality function deployment, QFD, to segment user requests into actionable engineering data. The process identifies normal requirements, the explicit features a user directly asks for, like a specific search tool. It then extracts expected requirements. These are baseline assumptions, such as data security and uptime, that users consider so obvious they forget to mention them. Finally, QFD uncovers exciting requirements. These are capabilities derived from engineering domain analysis that provide value the user didn't know was possible. Building only what is explicitly requested leads to software that meets the contract, but fails to provide a competitive advantage. QFD translates a user's operational perspective into a robust engineering baseline. Categorized lists are only the first step. The team must test how these requirements interact in a live environment. Engineers use use cases to map these interactions into a specific thread of usage. A use case defines the relationship between an actor, the human or system initiating a task, and the precise system response required to complete it. Mapping these pathways allows the team to observe system behavior under different triggers and environmental conditions. Tracing these threads step by step identifies missing functionality and potential logic gaps that remain hidden in static lists. A blueprint based on usage threads provides more resilience than a simple checklist of features. The final step involves converting the human-readable use case into a structural software design. Engineers perform a grammatical parse on the use case script, extracting the nouns and noun phrases. These nouns become analysis classes. They represent the business domain entities, like transaction or sensor, that the system must manage. Mapping the relationships between these classes provides the bedrock for object-oriented system design. This process demonstrates that informal user stories contain the structural data needed to define the software's architecture. The complete requirements model integrates the data from JAD sessions, QFD analysis, and use cases. The model is viewed through three panes: the scenario pane, the information pane, and the behavioral pane. Cross-referencing data across these three layers identifies contradictions and omissions that are invisible in a single-plane analysis. This model is a dynamic snapshot. It updates as the software team and stakeholders acquire more information about the problem. Requirements engineering functions as a continuous diagnostic tool, adjusting the project's trajectory as new information surfaces. Large-scale software applications are characterized by emergent requirements. The boundary between a software system and its environment is unstable. External pressures, like new regulations or changing user habits, force the system to adapt. Rigid, traditional specification documents often cause projects to fail because they cannot adapt to these emergent pressures. Active elicitation and dynamic modeling allow the software structure to withstand shifting requirements. A successful project results in an architectural model built to absorb continuous change.